In this video, we're going to wrap up Chapter 4, where we've been talking about the mechanisms going on behind classical conditioning. Our next topic is the idea that Pavlovian or classical conditioning can modify our responding to that unconditioned stimulus. Up to this point, we've pretty much just considered our conditioned response as something new, something that was happening separately. But this idea is basically to think of our conditioned response as something that helps an organism cope with the unconditioned stimulus. Maybe it's enabling an organism to interact with that unconditioned stimulus more effectively. So let's use an example we've talked about already, which is that eye blinking response to a puff of air. Being hit in the face with a puff of air the first time is something that you should have a startle response to, that you should blink in response to. But if it's happening constantly, it can get in your way of functioning in nature. Maybe it's a windy day, and it doesn't make sense for you to sit there blinking vigorously every time the wind blows. So it makes sense over time for you to have a reduction in the intensity of that eye blinking response because the same thing's happening over and over again. So our conditioned response could be to lessen the intensity of that unconditioned response. Now that situation of the eye blink response is an example of what we would call conditioned diminution of the unconditioned response. And here, diminution is just a fancy way of saying a reduction in the size, the extent, or the importance of something. So if we are reducing the size or the intensity of our unconditioned response, we are diminuting it. I can't stress how many times I've had to look up that pronunciation today. But if we want our formal definition here, we can say that that is a reduction in the magnitude of response to an unconditioned stimulus caused by the presentation of a conditioned stimulus that has been conditioned with that unconditioned stimulus, which apparently didn't make it onto my slides, but that should be unconditioned stimulus there. Basically, we're saying that our conditioned stimulus is getting us to learn that we should have a reduced response. Our conditioned response should be a less intense version of our original unconditioned response. Now, a standard example of this conditioned diminution of the unconditioned response would be something like conditioned drug tolerance. Now, we talked about the opponent process theory back in Chapter 2, and at the time, I'm pretty sure we also talked about drug tolerance as well. But we can also think of drug tolerance and view it in terms of classical conditioning. To set this up as a classical conditioning situation, we can look at each stimulus event or each time an individual drinks as an individual trial. So here our unconditioned stimulus would be taking in alcohol. The unconditioned response would be our A process and the physiological response to drinking alcohol, what our body does when it breaks down that chemical. Our conditioned stimulus would be anything related to drinking, so seeing the alcohol beforehand or a place that you associate with drinking alcohol could become a conditioned stimulus. And our conditioned response would be like our B process, where we start to counteract the physiological response to alcohol from the A process. Now, over time, this opponent B process comes to be elicited by our drug-conditioned stimulus, seeing alcohol or being in a place that we take part in alcohol. And it helps to substantially reduce the effect of our unconditioned stimulus. It helps to reduce that unconditioned response. So if we look at our graphs down here, which is the same opponent process graph as always, where we have our when we are drinking alcohol, so this would be our trial duration. We see our A process, which is the thing that is driven by drinking alcohol. So just from our unconditioned stimulus, that's the unconditioned response. This B process is driven by a conditioned response, and then we can see our net responding overall. And this reduction in what the A process could have looked like down to what we actually end up observing when we combine the A and the B processes would be that conditioned diminution of that unconditioned response. Now, all of those labels are on the next slide, just in case it didn't quite make sense to have me just say them out loud to you. They're all listed here. Using this new framework, we can start thinking about tolerance being attributed to our compensatory mechanisms, our conditioned response, as we try and return the body to homeostasis. And we can even go one step further and note that this conditioned response is driven by our conditioned stimuli, cues in our environment that are related to drug taking, alcohol taking. And then this kind of goes along with the idea of something like an overdose, or basically when our tolerance doesn't kick in, if our conditioned stimuli, if those environmental stimuli aren't present, then our body doesn't elicit these conditioned responses, these physiological effects to counteract the drinking or the drug use. So in a new environment that doesn't have the conditioned stimuli, those environmental cues to trigger that conditioned response, that counteracting measure against the alcohol or drug use, then we can see a much larger unconditioned response, a much larger drunkenness or effects of the drugs, which if you're used to having some kind of tolerance, having that go away because of this lack of conditioned stimulus and conditioned response can lead to things like overdose or severe intoxication, depending on the situation. And then this diagram here is just an example of what this here would look like with real-world data. So this is a more, or I guess a less structured view of what drug tolerance would look like, where we can see a response to the drug before conditioning. So this would be our normal physiological response. That would be this unconditioned response, because it's just the physiological effects of the drug. Then we have our B line is our response to the conditioned stimulus after conditioning. So that's our response to the environment, meaning that's going to be our conditioned response. So this is our US and this is our CS. And if we combine the two of them together after conditioning has happened, we can see our response to that original conditioned stimulus after we've been conditioned, after our conditioned response has come into effect. So we see a much reduced response to that drug, and we can call that drug tolerance. For some more real-world examples here, we have a study that was looking at individuals who either did or did not have history of cocaine use. So our group here, cocaine, they had experience in the past with having cocaine. Then the drug-naive group had no experience with any of those drugs. And then people in both groups were exposed to stimuli that were related to either cocaine, heroin, or non-drug stimuli. These kinds of stimuli would be things like environmental stimuli, so CSs. So they used for cocaine, people talking about using cocaine, watching videos of people buying and using cocaine, or asked to go through the motions of using cocaine. For heroin, same thing, but with heroin as the focus. And for non-drug stimuli, they just found control activities that they would ask you to watch videos of people doing sort of non-drug related things, or to think about doing non-drug related things. And so after this exposure to those environmental stimuli, to those conditioned stimuli, they measured a mean change from baseline for different kinds of physiological responses, so heart rate, blood pressure, so on and so forth, as well as self-reports of feelings of how much they wanted to do any of the drugs that they were being discussed. And you'll notice from these lines, only the cocaine group showed a positive change from baseline. And they showed that positive change from baseline specifically to cocaine stimuli. Everybody else showed either neutral or going down, a decrease in baseline, so maybe they relaxed. But the only significant difference here is this one here, showing that individuals who had pre-exposure to cocaine had a physiological response to cocaine stimuli. So this bar that goes up is actually us being able to physically see a conditioned response. Nobody else had that conditioned response. So this would be an anticipatory conditioned response. All right, let's move on from that topic and keep moving through our outline here. So we had started talking about what makes effective conditioned and unconditioned stimuli. So that's our CS and our US. We then moved on and talked about determining the nature of our conditioned response. That's our CR. So now the last part of the chapter is actually talking about how we associate those things together. So how do we actually connect our conditioned stimulus and our unconditioned stimulus? How do we make that connection? How does that association form? And we'll even talk about situations where that connection doesn't form. Sometimes a neutral stimulus doesn't become a conditioned stimulus. So we're going to look at what happens to either make it become a conditioned stimulus or what keeps it from becoming a conditioned stimulus. So the first of the things we're going to talk about is blocking. And a blocking effect is describing the interference of the conditioning of a novel stimulus because of the presence of a previously conditioned stimulus. What we're basically saying here is that learning something about one stimulus can block or prevent subsequent learning about a second stimulus. So if you learn something about stimulus A and then try and learn something about stimulus B, what you already know about stimulus A can get in the way and interfere with learning something about stimulus B. And we'll look at some examples and the procedure for that in just a second here. But first, we want to touch on why is this such a big deal? And the reason is, before someone proposed the idea of blocking, the consensus in the community was that temporal contiguity, things occurring together in time, was considered to be sufficient for learning associations. Basically, if you paired a CS and a US, then it should automatically become associated. That CS should automatically come to elicit conditioned responses. There was no sort of contingency in place for them to explain situations where it couldn't work. So let's look at the procedure, this blocking procedure, and see what they're talking about. So the blocking procedure involves two different phases. The first phase is going to be like a pre-training phase. And we're going to have two groups here, an experimental group and a control group. We're going to look at the experimental group first. So our first phase for our experimental group is to take stimulus A and pair it with an unconditioned stimulus. So A starts as a neutral stimulus and will become a conditioned stimulus the more and more it's paired with that unconditioned stimulus. So by the end of phase 1, stimulus A should be a conditioned stimulus. So here we would say that A becomes a CS. For our control group, instead of having this pairing of A and an unconditioned stimulus, A and the unconditioned stimulus are unpaired in that control group. It means that they'd have exposures to A and they'd have exposures to the unconditioned stimulus, but they were never temporally linked. They're never associated. So here, A is still a neutral stimulus. So for the experimental group, they have learned something about A, and our control group hasn't learned anything about A yet. Then we're going to move on to phase 2. And phase 2 involves pairing a compound stimulus with an unconditioned stimulus, the same stimulus as before. So A, we already know something about in our experimental group. B is going to be a novel stimulus. So B starts as a neutral stimulus, and A starts as a conditioned stimulus. For our control group, both stimuli are going to be starting as neutral stimuli. So we don't actually know anything about A in the control group yet. So we're starting from a different point of view here. And so we do multiple pairings. So we have our compound stimulus that's paired with our unconditioned stimulus. And down here, same compound stimulus paired with the unconditioned stimulus. And afterwards, we would enter our testing phase. And this is when we ask, okay, what have you learned about B? What we tend to find is that for our control group, where both A and B started as neutral stimuli, we find that B is now treated as a conditioned stimulus. Because going through this pairing, we learned that B is paired or associated with the unconditioned stimulus, so B becomes a conditioned stimulus that elicits a conditioned response. However, for our experimental group, B tends not to elicit a conditioned response. So it doesn't give us a CR, which tells us that B is still a neutral stimulus in this situation. And we can say that what we knew about A and the fact that we knew that A was associated with that unconditioned stimulus blocks any new learning for stimulus B. So stimulus B stays a neutral stimulus because of what we already knew about A. Now, this is a little bit of a complicated process, so we're actually going to do another example, a real experiment that's been conducted to look at this again. But it's going to be the exact same kind of procedure, just this time with an actual stimulus shown to you. All right, so this experiment was done by Pradas in 2011. And I really hate the way that they've drawn their diagrams. This triangle, no matter how you adjust the scaling on their image, it always looks like an equilateral an equilateral triangle, but it's actually supposed to be an isosceles triangle, where this angle is supposed to be different from this angle. They just don't necessarily make that super clear in the diagram, so I always point that out at the beginning because sometimes that helps grasp what the heck they're talking about. All right, but that out of the way, we have what looks like a very similar setup to what we just saw on the previous slide. So we have phase 1, phase 2, and a test. Ooh, what? So phase 1 here is that we have our experimental group or our blocking group who are taught that in this isosceles triangle, clicking in this particular corner would get them the sound of clapping. It's the right thing, they did right, they get cheers and clapping. If they click in the wrong corner, they would get the sound of an explosion. Now, during this phase 1, they wouldn't just give them a triangle and ask them to pick the bottom left-hand corner. They would have different angles for the training so that they could rotate the triangle so that you always knew that, say, the angle that was 30 degrees is always correct. And so sometimes it would be facing this way, sometimes it would be the opposite with the base at the top, sort of different angles so that you learn that that specific angle is what's associated with it being correct. For our control groups, they weren't taught anything about this triangle or the correct angle. For phase 2, this is when they introduce our second stimulus. So this is our compound stimulus phase. So instead of just having triangle A, as in the first phase, now they would have A and B. We're going to come back to control group 2 in just a second here. But, so for our blocking group and for control group 1, in this phase, there would be a corner that was marked as correct. And this corner could be predicted using the angle that they were taught in phase 1, or by looking at this second triangle that's been introduced in phase 2. And then for our control group 2 at the bottom here, they were never given triangle A. They were only taught triangle B and shown which was the correct corner in triangle B. So they're kind of there as an extra control, even for our control group. Then we moved on to our testing. And of course, for each of these, they get multiple trials so that they would learn where the correct corner was. For the testing, they were given only triangle B. So exact same as our blocking setup here. Start with stimulus A, given a compound stimulus A and B, and then they test with only B. So start with A plus B, test with B. And so now they could see, okay, how many individuals would get the right corner using only the information from triangle B. For the group that was trained on triangle B and tested on triangle B, they did really, really well. 92% of people in control group 2 got it right, which kind of makes sense. They were tested and trained in exactly the same setup. For control group 2, when they were given both triangles in their training phase here, but didn't have any prior knowledge, they still did pretty well. About 80% of them figured out what the correct angle was just from what they had learned about triangle B in this compound stimulus phase. But the cool part where we actually see blocking occurring is in our blocking group, where we saw that only 20% of people could guess the right corner based on triangle B. So here, what they knew about triangle A from their pre-training here interfered with their ability to learn anything new about triangle B. So when they're tested with only triangle B, when they don't have triangle A to rely on, we see that they learned much, much less. So there was blocking here. So why does A block B? The proposal is that the unconditioned stimulus needs to be surprising or unexpected to be effective in producing learning. If that unconditioned stimulus is signaled by a previously conditioned stimulus, if A is already telling us everything we need to know, then it isn't surprising. We're not learning anything about B because what we already know about A was sufficient to explain what we were seeing. So the effectiveness of our unconditioned stimulus and our surprisingness, and its surprisingness, is what ended up contributing to what we call the Rescorla-Wagner model. Now, the Rescorla-Wagner model is only one of many different models of associative learning. It is one of the most popular or most common ones, but it doesn't explain everything. So we're going to talk about each of these 4 different categories of models of associative learning, and we'll break them down just a little bit. I will note that we could spend an entire class on each of these types of models. They can get very, very complicated, and different people in different fields will prefer to use one or another of these models. So there can be disagreements as to what is the best or most correct model. But what we're going to find is that each of these models tends to do a very good job at explaining some things and then has gaps where it can't explain others. So we have to keep in mind that none of these models is going to be wholly correct or wholly capable of explaining a full situation. So let's start with our Rescorla-Wagner. The basic premise behind the Rescorla-Wagner model is that the effectiveness of an unconditioned stimulus is going to be determined by how surprising it is. Basically, in a given trial, the more surprising that unconditioned stimulus is, the more we're going to learn about it in this particular trial. And we can quantify these variables, how surprising stimulus is, how much we can expect to learn from that stimulus, and so on. We can put that all together into a mathematical model where we can actually calculate out how much learning we see on a trial-by-trial basis. So let's talk about each of the components here. First, we have our delta V. Delta meaning change in, if you're familiar with mathematical terms. It tends to use for change in. So for us, delta V is a trial-by-trial change in associative learning strength of our unconditioned stimulus. Basically, how much are we learning about that unconditioned stimulus each trial? So the larger our delta V, the more we've learned in that particular trial. K is a constant. Depending on how complex of a model you are looking at, sometimes you'll see it represented by multiple terms. So sometimes you'll see it as alpha, sometimes you'll see it as beta, sometimes you'll see it as both alpha and beta. We're going to simplify it and consider a constant related to the overall salience of our unconditioned stimulus. Basically, how attention-grabbing, how important is this stimulus? The larger the K is, the more salient that unconditioned stimulus is, the more learning you're going to tend to see each trial. That kind of links back to what we had talked about earlier as to what makes a good unconditioned stimulus. More salience means you're going to learn more about it. Our lambda here is an indicator of the maximum possible associative strength of our unconditioned stimulus, which is a fancy way of saying this is what occurs every single trial. So this is what is supposed to happen every time. And then V, without the delta this time, is going to be our current associative strength of the unconditioned stimulus. This is what we expect to happen based on what we've experienced in the past. So if you have no experience at all with this unconditioned stimulus, then your V starts off at 0 because you have no expectations, you don't have anything to expect. As you learn more and more and more, as you've acquired more knowledge, that V gets larger and larger up to a maximum of lambda. So if we have lambda minus V is 0, so if lambda and V are the exact same amount, that means that we expect exactly what ends up happening. So our expectations and what happens match, and then there is no surprise in this particular trial. So this term here, the difference between what occurs and what we expect, the difference between lambda and V, is effectively the surprisingness of our unconditioned stimulus. So the larger this term ends up being, the bigger the difference between lambda and V, the more we're going to end up learning because it's more surprising. Okay, so let's look at the graph that goes along with this, because I find that some of these concepts, again, are a little bit abstract, so it helps to go over them a couple of times. So let's orient ourselves on this graph. At the bottom we have trials, which is our time measurement, and then up the y-axis we have associative value, that's the V, how much we have learned about this particular stimulus. At the very beginning, we have no associative value. We know nothing about the stimulus, so we start at 0. And at the beginning, our lambda minus V is going to be pretty much just lambda. If we know nothing about this stimulus, if our V is 0, that term is just lambda. So that is as big as that length can get. And then over time, we're going to be learning, we're going to continue to learn, but as our numbers, as our associative values get larger and larger, as we get closer and closer to lambda, we're going to be learning less and less each trial. So the slope gets less steep and less steep and less steep until we finally get to the point where lambda and V are the same when they're equal, when what we've learned is what is possible to learn. And then we're going to sort of sit at no slope, at we know exactly what we need to know about this situation. So early on, there is a large value for lambda minus V. So we see a lot of learning, we see a steep slope. Later in training, lambda and V are much closer together in number, and so we see much less training, so much less learning. And so the slope gets less steep, and we see less of a jump in between trials. So let's move on and look at this Rescorla-Wagner model in practice. So let's look at how Rescorla-Wagner can predict blocking. So this is our standard blocking procedure, same as what we've just seen a couple of times over now. If we look at our experimental group, after phase 1, they've learned about A. They've gone through this whole process so that they've learned everything. They have a V of lambda for stimulus A. And so because A completely matches what they expect in that situation, because in that situation, lambda minus V is going to be 0, they know everything about A. And when we adjust the term to include B, so now we have A plus B, VA on its own was already lambda, so adding in the B term doesn't really change anything. Our lambda minus V is still going to be 0. We see no conditioning or no learning about B in this experimental group because A already perfectly predicted our unconditioned stimulus. So here, if we looked at VA on its own, VA was lambda because we already learned everything about A and there's no surprise there. VB, we don't know anything about B at all. We have 0 knowledge about B. We're starting at the very beginning. But if we plug that into the equation, our lambda of what's going to happen minus what we know should happen from A and the nothing we know about B, it still turns out to lambda minus lambda is 0 for the mathematically inclined individuals. I find the logical explanation of if A explains everything and if A or V of A is lambda, we've already explained everything that can be explained in terms of lambda. So we see no learning to B, and that fits with our Rescorla-Wagner equation. Now, as I said, we could spend an entire class talking about Rescorla-Wagner and how it applies to different situations, and there can be classes where you go through and calculate out tons of different things like this. We don't have the time to delve into it in that much detail. So I'm not going to expect you to be able to do massive calculations to apply the Rescorla-Wagner equation to each of these situations. Just sort of understand the idea behind the model, but don't expect to have to do lots of calculations. I just find that some students get hung up on the equations, but I'd be much more likely to talk about it in broad terms of something being very surprising or not surprising. Or I would tell you that the V is the same as lambda or not the same as lambda. So the very basics of interpreting the equation. All right, on that note, we're going to talk very, very briefly about something else that the Rescorla-Wagner model can explain, and this is conditioned inhibition. Now, if you remember, conditioned inhibition has 2 different trial types. Trial type A happens when our CS plus is followed by an unconditioned stimulus, usually something aversive. And then trial type B has our CS plus paired with a CS minus, and there is no unconditioned stimulus here. In order for the Rescorla-Wagner model to work here, we actually have to consider the reinforced and unreinforced trials separately. So we can have our CS plus information at the top and our CS minus information at the bottom. And that fancy footwork continues where we have to assume that our CS minus has a negative associative value so that the sum of our CS plus and CS minus can have a net of 0 later on in the model. So that's why the CS minus goes downward and the CS plus goes upward, because they're kind of acting in opposite directions to one another, one being excitatory and one being inhibitory. So that's our basic setup here. The next thing that we want to note is that at first our net view, so this is our combination of CS plus and CS minus together, the first thing that we see is that there's actually a little bit of a positive bump there. So even though we have our inhibitory conditioned stimulus playing, we're still going to see a reaction as though we're only expecting the CS plus. And this happens because we need to learn something about the CS plus before nothing happening means anything. So basically, our CS plus first becomes associated with the unconditioned stimulus. So we start seeing this one rising quite a bit faster. And then we need to have that anticipation, that expectation that the CS plus is associated with that unconditioned stimulus in order for the CS minus's presence to mean anything. Just throw the equation up here to help explain what I'm talking about. So in these B trials, we have these two stimuli playing and nothing is happening. So our lambda is nothing and our expectations would also be nothing. So the expectation and what happens at the very beginning for our B trials is nothing. So we need that learning, that type A trial learning to happen at first. So for the type A trials, we learn that something is going to happen when the CS plus plays, and what is going to happen is that unconditioned stimulus. So that's where we learn what is going to happen. And our expectations start changing to get closer and closer to lambda, just like normal. Once we start learning about what we expect when we hear or see this CS plus, that's when we start learning something new in these trial B types. So once we've learned that the CS plus is associated with the US, then when we have a CS plus here, we expect a US, but it doesn't happen. So our expectations are different from what actually happens. So for those trial Bs, we're expecting something to happen, but it doesn't. So our V is larger than our lambda, which leads to a negative term in the brackets there. And that's how our CS minus acquires that negative associative value. And so once we've learned a little bit about the CS plus, then we can start learning about the CS minus, and that's why we see that little bit of an upward bump at the beginning for associative value of our CS plus and minus together. But over time, as we've learned how this system works, our net CS plus and minus becomes 0 because basically our CS minus comes to cancel out what we know about the CS plus. Hopefully that extra explanation helped clarify that just a little bit. I found it's a little bit confusing in the textbook as well. But you need to learn about the CS plus before you can start learning about the CS minus with the Rescorla-Wagner model. All right. Our next thing to consider is the extinction of conditioned inhibition. Now, in this situation, the Rescorla-Wagner model is actually fairly problematic. It doesn't do a great job explaining conditioned extinction here. So we have basically the graph that we had just been looking at, where we have our CS plus and our CS minus, and they equal each other out, so that the CS plus plus the CS minus is 0. That's been set up during acquisition. Extinction is just that we would present the CS plus and the CS minus in the absence of our unconditioned stimulus. And if we plug those numbers into the Rescorla-Wagner model, we get this nice clean curve where the CS minus will sort of increase and the CS plus will decrease, and they'll both come together and eventually meet at 0, balancing each other out the whole way. And so what this would mean is that we'd see sort of normal extinction to the CS plus, and the extinction of the CS minus would look like a loss of inhibition. So you would stop seeing the CS minus as a conditioned inhibitor. In practice, that's not actually what we find. In reality, if you present the CS minus without the US, then it actually becomes a stronger conditioned inhibitor. So this doesn't really match up with what's in the real world. This model views extinction as the reverse of acquisition, but it definitely is not the reverse of acquisition. what's really going on is that we're learning a new relationship between the CS and the US when extinction is happening. So Rescorla-Wagner model doesn't do a great job explaining this extinction. And we're going to come back and talk about extinction quite a bit more in Chapter 9. So just be aware that this is one of those things that the Rescorla-Wagner model does a very bad job of explaining. Now, the Rescorla-Wagner model is what is commonly taught and commonly used in North America, but of course, it isn't the only model or type of model that can be used to look at this kind of behavior. In fact, if you're in Britain, the British psychologists tend to use attentional models. And there's a couple of very closely interrelated subtypes of this model, so we look at them all together. I'm just going to talk about them very briefly because while they're not commonly used in North America, it is still a good idea to be aware that they do exist if we're looking at literature from other places. Some of the key differences between these models are that while the Rescorla-Wagner model focuses on our unconditioned stimulus, our attentional models focus more on the attention-getting properties of the conditioned stimulus. And within these attentional models, the amount of attention that we pay to that conditioned stimulus is going to change depending on how surprising the unconditioned stimulus was on the previous trial. So if the unconditioned stimulus in the last trial was very surprising, we're going to pay more attention to our conditioned stimulus on the trial that follows. If our conditioned stimulus had been followed by an unexpected unconditioned stimulus, we pay more attention. But if it's followed by an expected unconditioned stimulus, if it's something that we knew was going to happen, if it doesn't surprise us, then we're not going to pay attention to the conditioned stimulus the next time around. And that also leads us into another key difference between the attentional models and the Rescorla-Wagner models, and this is that our attentional models are paying attention to future trials. So we assume that the surprisingness of our unconditioned stimulus will alter how much attention we pay to the conditioned stimulus in future trials. Whereas the Rescorla-Wagner model, we look at the surprisingness of our unconditioned stimulus within a trial, and it's going to determine what is learned about that unconditioned stimulus in the same trial. So if we're telling them apart, our Rescorla-Wagner is going to stay focused on the unconditioned stimulus. It's focused on same trial learning. Attentional models are going to look at the relationship between the CS and the US and are going to look at how our attention changes between trials. So looking at how what we've just learned will affect future trials. So quick and easy way to tell those two models apart. The next model that we're going to talk very, very, very briefly about are the relative wait time hypothesis, or relative waiting time hypothesis. Now, there are a bunch of different models that explain timing and the information that we get based on timing, but we're going to talk very, very briefly about it here. Mostly it's important to mention them because neither of the two models that we just discussed can actually account for the effects of timing on conditioning. So neither the Rescorla-Wagner model nor any of the attentional models actually takes time into account. Now, in the previous chapter, we already talked about the temporal coding hypothesis, where we learn when our unconditioned stimulus occurs in relation to our conditioned stimulus, but time between trials is also important. So our inter-trial intervals, or the spaces between exposures, are also very important in determining what we learn. When it comes to our relative waiting time hypothesis, we're actually looking at a comparison between two time periods. So we're comparing how long you have to wait for the unconditioned stimulus during the conditioned stimulus. I can draw my little diagram down here, where we have our conditioned stimulus, which starts and then stops, and our unconditioned stimulus, which will start some point after the conditioned stimulus and stop sometime later on. That's the first thing that we consider. The second thing that we're considering is how long you have to wait for the unconditioned stimulus during an intertrial interval. So if we have a second trial that happens, so if this is our cutoff between trials, how long do we have to wait until we see a repeat here? Like that. And looking at sort of this distance instead. And our take home from this is that if this gap here, how long we have to wait for the US while the CS is playing, if that's a fairly short amount of time, then the CS is telling us something important about the US, and it makes sense to pay attention to it. Whereas if this distance is longer, if it's more like the distance between trials, then we're learning a lot less. The CS is telling us less about the US, and then we're not going to learn much at all. And just as an illustration of what that longer period could look like, if the start of our CS is very distant in time from the start of our US, then this longer interval means it's not telling us quite as much. Now, the last hypothesis or model that we're going to talk about here is the comparator hypothesis. So just like our waiting time hypothesis ended up introducing a new element to consider, the time, our comparator hypothesis gets us to consider other aspects of the experimental situation. So what else is going on outside of just our US and our CS? So this hypothesis acknowledges that there are other cues available to the animal while in this experimental context. And we can call those other cues comparator cues. So they are just other things in the environment that are also present when the target CS is being conditioned. So while you're learning an association between the CS and the US, you're also learning about the other stuff that happens to be going on in the background or in the environment. So if we want to sum it all up, this comparator hypothesis assumes that whether conditioned excitatory or inhibitory conditioning occurs will depend on the relative strength of the excitatory value of our CS, the thing that we were targeting, versus the strength of the comparators, those things in the environment, the context in which we learned about our target. So let's see this actually in action. Let's look at the comparator hypothesis and blocking, specifically so that we can compare it to Rescorla-Wagner. So if you remember, Rescorla-Wagner stated that in blocking, learning about the conditioned stimulus, B, our second stimulus, is what's blocked. So once we've already learned about one conditioned stimulus, A, then we have no reason to learn anything about our second stimulus, B. So the learning itself is what is blocked according to the Rescorla-Wagner model. However, this comparator hypothesis says that what's being blocked isn't learning about B, it's actually just the responding to B. So that's saying that the environment, the cues going on in the environment, or the context, is preventing what we have learned about CSB from being expressed. So what we're seeing is a sliding in the balance so that we're seeing a little bit more of inhibitory responding, so a lack of responding to B because of the things in the environment. So how could we test this? To do that, we'd have to remove whatever it is that's blocking our ability to respond to the conditioned stimulus B. So our basic idea here is that we have an issue of performance rather than learning. So it's the responding or the performance of a response to B that's being blocked, not a learning issue as Rescorla-Wagner would state. So how do we actually go about removing this block? We're going to use a process called reevaluation. So the idea here is that the thing that is blocking responding to the CSB is the presence of CSA. So let's remove responding to CSA. And so we could do our normal blocking procedure, phase 1 and phase 2, just like we've seen previously. But instead of going straight on to testing B, we introduce this reevaluation effect where we remove responding to A. And so what we're doing to eliminate that responding to CSA is to basically use extinction. So present our conditioned stimulus A with no unconditioned stimulus following so that we get extinction. And as responding to CSA reduces, then we can start testing for a response to CSB. So if after removing the responding to CSA, we see an increase in responding to CSB, then we would say that the learning of CSB wasn't what was blocked, but rather responding to our conditioned stimulus B is what was blocked. So the performance was blocked rather than the learning. And so that's where the test B would come in at the end. All right, that brings us to the end of a fairly information-dense chapter. So our big take-homes coming out of this chapter are that an animal's previous experience with both the conditioned stimulus and the unconditioned stimulus can have an effect on learning. The presence of other stimuli during a conditioning trial can also affect learning, as well as the relevance or the salience, which I almost forgot the word for, the relevance and salience of our conditioned stimulus and unconditioned stimulus can also have an effect on learning. And the last thing to keep in mind is that we can see learning happen without an unconditioned stimulus through either higher order conditioning or that preconditioning procedure that we talked about. So just a lot of stuff to keep in the back of your mind as we wrap up on classical conditioning, at least for now.